last time. I think what everyone suggested here was correct. The way to think of it is, and what we said at the end, that these things come with a sign, was correct. The way to think of it is that we had C on the upper half, using the doubling trick. We had C on the upper half plane and C tilde down here. But C and C tilde, it's just one continuation. Once we get rid of it, once we convert the upper half plane into the whole plane, we just have one holomorphic C. And so we just use the equation that C Z1, C Z2, C Z3 is equal to Z12, Z23, Z13, and then put the Z's equal to Y, and this does flip sign. Okay? And as we said at the end of last class, that cures all our problems. It gives us the right minus sign. Another pragmatic way to do it is to just, do whatever it takes to completely cancel the dependence of your positions, including signs.
And this will be Z31.
31, thank you. Including signs, and then the fact that you get a minus sign between the two factors is totally obvious, because apart from Z dependencies, which have to cancel, the amplitude was K12 dot epsilon 3. And this flips sign under. Yeah. So the physical part was antisymmetric. The other part has, if you do it right, it has to just completely cancel out, including signs. That's the confusing thing, right? Okay. Now, at the end of the last class, we were discussing 3-photon scattering in the superstring, and so let's quickly go through that. I hope the signs don't give us trouble here. Let's see. Okay, so if you remember, we had an epsilon1 dot psi. Epsilon 1 mu psi mu. That was the vertex operator of the first photon. We had an epsilon 2 mu dot psi, let's call it mu psi nu. And then we had a more complicated vertex operator. Okay. Both of these, of course, came with a, so this is at y1, this is at y2. Each of these came with an e to the power minus phi of y1, e to the power minus phi of y2. And then there was a zero picture vertex operator, which I'll read off from Polchinski. It's ix dot rho, let's say, plus 2 alpha prime k3 dot psi psi rho. Epsilon 3 rho. Okay, and then of course there is the C coast, which is just all the way. Okay, so let's work this out. Okay. So there are two terms. There's this with this, and there's this with this. Okay, so we had this, and there are also the e to the power ikx's, which I have not written, but of course are there. Right. So as we saw last time, so there's overall y12, y13, let's say 2, 3, y3, 1. That's from the C hosts. Then there was a 1 over y12. That was from the contractions of the e to the power phi's. Okay, so we've taken those into account, so now I'm rubbing that out. Okay, so we focus on what's important. Okay, then we had the guy that was from here. Okay, wait, first let's do the contraction of these two. So that made 1 over y12 square, and then give us an epsilon 1 dot epsilon 2, because the 2-point function, the 2-point contraction of two sides was because the dimension half fields. Okay, And in addition, then we had this term which was, now of course we have to get all the relative factors right, but being a bit careless about relative factors, which we had them on the board last time. I'm going to write it down and ask somebody if they can help me with the relative factors. This was k, what was it? So k1 mu, no, rho, by y3 minus y1 plus k2 rho divided by y3 minus y2. And if we don't take this explicit I, can somebody remember what the relative factor? What some I, I'll look it up. It's good. Here, minus 2i alpha prime. So with the explicit factor of I is 2 alpha prime. And y3 minus y1, y3 minus y2. Yeah, sounds good. Okay, so 2 alpha prime and then this. And then the remaining term is whatever we get from here, 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 here. Here this x dot has gone. So we've got a plus 2 alpha prime because the vertex operator came with a 2 alpha prime. Now, as we discussed last time, we're going to have two kinds of contractions. This guy with this guy and this guy with this guy, or vice versa. Clearly, since the contractions involve a flip, say, let's say I contract this with this and this with this, there's no sign. But if I contract this with this and this with this, there's a sign. Okay? So there's a relative minus sign between the two. What are the two terms? The term in the way that I've written it here is 2 with epsilon 2 gives a k3, and so let's do that carefully. So the first term is epsilon 2 dot k3 and epsilon 1 dot epsilon 3. Now, what about the factors of y's? This was y12, y13 and y23. Right? Because now the contractions this way get the same y12, y13, y23. Same, but there's a minus sign. Okay, so this is minus epsilon 1 dot k3 and epsilon 2 dot epsilon 3. Okay, so let's put it all together. So there's y23, y31 by y12. Okay, and then there was epsilon 1 dot epsilon 2. Okay, there was epsilon 1 dot epsilon 2 into y32. Now y32 minus plus y. What? Yeah, firstly I missed some epsilons here. Yeah. This was k1 dot epsilon 3, right? This was k2 dot epsilon 3. So let's make this k12 dot epsilon 3 by 2. And this is minus k12 dot epsilon 3 by 2. Is that good? And now this is y3 minus y2 minus y3 minus y1. So this is y12 divided by y12 divided by y31, y32. Okay? And this character,
The K12 over 2.
yes, times K12 dot epsilon 3 divided by 2. Okay. Now this, okay. What is the dimensionality doing here? This one had, what, sorry, say again? There's an extra y12 in that as well, you're saying. That factors just overall, I would say. Thank you. Let me write it again. Epsilon 1, epsilon 2, let me just check that. No, the epsilon 1 dot epsilon 2 is not inside, right?
Y12 in the first term.
Yeah, let me just check. So when we did the first term, we were doing this guy. So we got the epsilon 1 dot epsilon 2 from this guy. And we got the y12 because this contracted with this. And then we got an extra factor of these guys.
Y12 don't come in the next.
Thank you. You're saying this should just have not been here.
Yes.
Okay.
And the Y12 will be inside.
And then there's a 1 by y12 here. Okay. And then there is a plus. Now let's look at that. Let's take the 2 alpha prime out. It's not even here. 2 alpha prime. And let's then take this overall factor of 2 out also. Okay. So this quantity is epsilon 1 dot epsilon 2 by y12 to k12 dot epsilon 3. And this quantity now, let's look. This is
Y12 cancels. Every Y cancels, right?
yeah, every y cancels. Every y cancels. Exactly. Yes. Thank you. So this we just cancel it. Right. And these two of course cancel here. Right. And they also cancel
That
here.
yes.
So every y, exactly, as you said, every y cancels. So we just get rid of them. There's just an alpha prime. And now we have to keep track of these guys carefully. The guys we got from this structure. So that was epsilon 1 dot epsilon 3. So let's write it properly. This is k12 dot epsilon 3. Then we got plus epsilon 1 dot epsilon 3 into epsilon 1 dot epsilon 3 into k3 dot epsilon 2. So k3 dot epsilon 2, so k31 dot epsilon 2, and then that's correct with a factor of half because we've taken that factor of half also. Okay, and then minus epsilon 2 dot epsilon 3 into k 3 dot epsilon 1, so k31 dot epsilon 2, epsilon 1, k32 dot epsilon 1. Okay, excellent. Now this is one of the two terms. This is the term that we got when we put y1, y2, y3. We have to add the other one as well. Okay, but first let's look at the symmetry of this term. Okay, this is k12 dot epsilon 3 plus,
The last term should be K23. Then it is yes.
So it's plus K23,
That's an S3.
and this is nice and cyclic, you're saying, right? K12 dot epsilon 3 plus K31 dot epsilon 2 plus K23 dot epsilon 1. So this is cyclic. However, cyclic sums are not completely permutation invariant. We want something that would be completely permutation invariant. Okay? But what we need is, so cyclic sums are, under S3, and the permutations of three elements, that are the cyclical permutations. So S3 is a 6-dimensional group, permutations of 3 elements. There are there's identity, there's cyclic permutation by 1, cyclic permutation by 2, and this is obviously invariant under that.
This is S3 not Z2.
Exactly, but there are also the exchanges. Okay, so we need the other 3 guys that will account for the exchanges, and that will come from the other diagram. Okay, so the other diagram will give us, so I suppose this times just any 1 goes to 2 interchange.
Yeah, actually that will be the negative of.
1 goes to 2 interchange.
Flip the first sign.
Yeah. Now,
And then
yes, it will flip every sign, but remember, exactly, it will flip every sign, perfect. But remember that this came with the trace lambda 1, lambda 2, lambda 3. And therefore, we'll just get this with the commutator. Okay? The fact that it just gave you 0 when there were no lambdas is a famous statement. The famous statement is just kinematically, there is no
one photon cannot be. Oh yeah.
Yeah,
Three
there is
photon vertex.
the 3 photon vertex vanishes. However, the 3 gluon vertex, of course, does not vanish. Okay? Now, what is this 3 gluon vertex? Can we see do we know the Lagrangian that it comes from? Yang-Mills. See, Yang-Mills Lagrangian. Yang-Mills Lagrangian, it's a very strange thing if you think about it, because it's first order derivatives. Okay? But that's exactly the structure of the 3 gluon vertex in Yang-Mills. Because we have del mu A plus let's say, A commutator A. So mu nu, the whole thing squared and trace. If we want 3 photons, we have to take the quadratic term from one guy and the linear term from the other guy. So it's sort of like trace del mu A times A nu times A mu commutator A nu. Okay? And now what you have to do if you want the Feynman diagram, the vertex, you have to sprinkle particles 1, 2, 3 in every possible way. In this guy, every one of them will give you a derivative contracted with some vertex, with some, in this case it would be K1 dot epsilon 2, but there will be all such terms. Okay, and then there will be an epsilon dot epsilon. That's what we're seeing here. K dot epsilon and epsilon dot epsilon. Of course, it's going to give you something completely symmetric. It'll give you this thing. Okay, so what we're seeing here is something quite marvelous. The thing that we're seeing is that the 3 gluon scattering amplitude, that we're getting from string theory. Okay, the 3 gluon scattering amplitude that we're getting from string theory is simply precisely that you got from Yang-Mills theory. Okay, now at 3-point function level, this is not such an amazing thing. Okay, because as we've repeatedly discussed in this course, 3-point functions are highly constrained by kinematics. Something that's more remarkable is it turns out, and I'm not going to do the calculation in detail. Okay, I'll leave this for you as an exercise. But if you compute the 4 gluon scattering, We'll compute 4 tachyon just now. Okay? But if you compute the 4 gluon scattering, okay, it turns out that the structure from that the index structure from that is also precisely the index structure from 4 gluon scattering of Yang-Mills theory. So let me say that again. You know, in Yang-Mills theory, the index structure, the polarization dependence is something. Now in string, and then in 4 gluon scattering, there are many possible kinematically allowed polarizations, each of which could come with their own functions of ST and U. So in general, what you would have expected is one function of STU times some polarization, plus another function of STU times another polarization, and all of them come in a way you can't factor out some common structure, because each structure would have come with its own function of STU. And you would have expected in general some mess. And if you do 4 gluon scattering in the open bosonic string, it's a mess. It's exactly what we discussed. You get very complicated looking answers. Each structure comes with its own thing. However, when you do it with a superstring, you find that there is an overall structure and some function of STU. Now, once I've said that, it had better be that that overall structure is that of Yang-Mills theory. Why had that better be? Because we expect that at very low energies, gluon scattering reduces to Yang-Mills scattering. So if there's just an overall scattering structure, then that structure will also appear at very low energies. So the index structure better be that of Yang-Mills theory if the statement is to be true, and indeed it is. So it's a very simple scattering amplitude. You know, because complications of these scattering amplitudes are usually with particles with polarizations are usually in the index structures. This has a very simple index structure overall outside, times the kind of STU function that we saw in Virasoro-Shapiro amplitude, products of gammas. But the thing that makes this really simple is that it's very simple structure just overall outside this. Okay. It's not too hard to do this calculation. It's basically this kind of calculation. You have to put 2 of these and 2 of these now. Right, because two minus 1 picture vertex operators is always the rule. You have exactly 2 minus 1 picture vertex operators because you have to absorb the background charge. You need 2 e to the power minus 5. Okay, and then do the contraction. So it's some work, but when at the end of it you get a very nice, beautiful answer out of it. Very unlike the bosonic string, just another sort of indication that something good is happening. Okay. Also, the fact that you get at low energies for 4 gluon scattering, Yang-Mills theory on the nose. So, of course, another consistency check, right? Because you would have expected it on general grounds. But these kind of calculations have to make it work. And it's very different from saying from effective field theory we expect this. But we're not doing effective field theory. Some of this vertex operators, world sheet, signs of sea coasts, all kinds of weird stuff is happening. At the end of it, we get the same scattering amplitude as Yang-Mills theory. These are the kind of things that make you feel we're onto something when we study string theory.
Why is it not surprising that we don't get it for bosonic string?
Why is it not surprising? You see, because unlike 4 point... Okay, so let's look at that for a moment. You see, unlike for 3-point functions, there are many possible Lagrangians you could have written down for the photons. Okay, one of them is like trace f squared, but you could also have written down something like trace f to the 4th, for instance.
No, I mean,
okay. Now, it's true that this will dominate as leading low energies because this is a 2-derivative object, whereas this is 4-derivative. So, if you take the bosonic answer and go to very low energies, of course, then you do get the Yang-Mills action.
Okay.
But the thing is that, you know, when you go to higher energies, you start getting new structures. It's not a contradiction with anything. It's some irrelevant operator that you could have added to your energy Lagrangian, and basically it's telling you that the bosonic string has this irrelevant operator. Now, not to say the superstring theory doesn't. It also does. Because
higher orders.
no, okay, it's true, also a bit higher order. But the important point I'm trying to make is that all the irrelevant operators for the superstring are those that give you the same structure of scattering amplitude, which is a bit of a miracle. You know the structure for the very low energies, and then you get just the same answer all the way. Actually, I don't know if you remember, but when we discussed gravity scattering amplitude, it was the same thing. It's not the case for the bosonic string. Yeah, that was 3-point amplitude. But if you remember, what we got was something like something square for the 4-point function. Okay, and that's something square had two derivative, it was like a square of a 1 derivative piece, a 3 derivative piece, and maybe even a 5 derivative piece. And then you took the whole thing and squared it to get the graviton amplitude in the bosonic string. And so then when you took the whole thing together, it became just some mess. Okay, but in the case of the superstring, it's just one structure, one homogeneous structure square, and then the gamma functions.
Yeah, but still 1 plus 3 plus 5 whole square, right? 3 structure plus
No, but it wasn't even that simple, because you see no, you're right. It's 1 plus 3 plus 5, but this 1 plus 3 plus 5 had, for instance, different okay, it's true that if you write it in some way, it looks like it's a whole square. But the factors have different powers of, let's say, st and u between them. So suppose you write them in terms of polarizations. If you wrote down the scattering amplitude, you would get epsilon dot epsilon blah 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 plus s square t square epsilon dot epsilon da da da. So what I'm saying is that the different polarization functions come with different functions of STU. They're very highly related functions. But because this term was 2 derivative, let's say, this term was 4 derivative, this term was 6 derivative. Yeah, okay. Let me back up. It's true. It is something square. But if you wrote it in terms of basis epsilons, the coefficients, the linear combination coefficients involve functions of STU. Okay? So knowing, right, I suppose all I want to say is that knowing the low energy answer does not tell you the epsilon structure, the scattering structure at high energies. Because the low energy structure will just pick out this part. But there was also this and this. So it was a square, but it's not like it came just from Einstein-Lagrange.
But can't we just write some action for this term and say, okay, the action contains only these 3 terms?
Yeah, you can. So what you can do is to ask, there is this, in general, there is a translation between scattering structures and Lagrangians. The counting goes as follows. In d dimensions, d greater than equal to 7, if we focus on parity odd structures, parity even structures, okay, then there are a total of 10 Lagrangians plus their derivatives. So the generic Lagrangians of the form RRR, these are all Riemanns with various weird contractions. And then there are derivatives contracting between them, del alpha, del beta. Now, these derivatives contracting between terms don't change the index structure because they just give you powers of ST and U. So the basic index structure is contained in the basic Lagrangians without having derivatives whose indices are contracted between derivatives. Note that derivatives whose indices are contracted with Riemann might generate a new index structure, because that's k is dotting with epsilon. Okay? But derivatives contracting between themselves don't generate a new index structure. Now you can show the following. You can show that every possible S matrix can be obtained from, so when derivatives contract between each other, I use the word descendant to describe this Lagrangian coming from some more basic Lagrangian. So you can show that every possible S matrix comes from descendants of 10 basic structures, Lagrangian structures. Now a descendant is just some function of STU. So basically then you can write down a Lagrangian term times these various derivatives, or a Lagrangian terms times its STUs. But in general you would need 10 structures. Of these 10 structures, 9 appear in the superstring. In the bosonic string. Okay. In some relatively random looking way. Whereas it's just one compact structure basically for Einstein. That's another way of saying it. Okay, any other questions, comments? Okay. Yeah.
So this means that you are saying that this superstring, in the case of superstring,
Yes.
low energy physics
It's telling you a lot about the high energy physics, but not everything. Because there's lots of information in polarization structures, but that's not all of it. You have to know the function of STU behind it. That is not. So what it's telling you is that graviton scattering in the superstring is as simple as tachyon scattering in the bosonic string. Because in tachyon scattering we had no epsilons because they were scalars. So all the fun was in the STUs. Now you might have thought, oh my, you're going to get new functions for every polarization structure. In the superstring that doesn't happen. Once and for all you take out the polarization, so it behaves like scalars. Okay? And then you get whatever you get. But of course that irreducible complexity of what, had it been for scalar scattering, that was always there. Okay. So let's very quickly go through open string tachyon scattering in the bosonic string, because luckily speaking the open string for tachyon scattering in the bosonic string, because we're doing this in the bosonic string because the superstring doesn't have a tachyon. We could have done something in the another way of saying it is that the 10-dimensional vector multiplet, the multiplet that lies on the D brane, the 10-dimensional vector multiplet has no scalars. Okay, it's just made up of at the n equals 1 vector multiplet. That's the thing that open strings vertex operators give you. It consists of vectors and spinors. Okay, so if you want to do for something scattering, you would have to deal with indices, which of course, because the final answer is so simple, it's not too bad, but it's a pain in the neck to actually do in class. Okay. On the other hand, the analog computation of that form in the bosonic string is nice, because you can just do it with the tachyons. There are just no indices in the game. So that's why we're going to work out the tachyons. Okay, so let's do that. So for the tachyons first, we will we will allow them to have their Chern pattern factors, because that's really the seriously new thing about open strings, the Chern pattern factors. Okay, so what we're going to have is let's call this y1, y2, y3, and y4 with polarizations lambda 1, lambda 2, lambda 3, and lambda 4. Okay. Now the first question we're going to ask is how many such diagrams are there? 6, exactly. Because you could have had 24 permutations, but there are 4 cyclic elements which are identity. So what we're doing is S4 mod these cyclic guys, which is some 6-dimensional group. It's basically S3. Okay, so we can think of it as keeping y1 fixed and permuting the other guys. Okay, so there are going to be 6 diagrams as you guys have pointed out, and let's look at, so let's start with one. So let's start with the one where we get trace lambda 1, lambda 2, lambda 3, lambda 4. Okay. Let's start with this guy and let's compute what we get. So this is very easy because it's e to the pi k dot x of sigma 1, e to the pi k dot x of, let's call it y1, y1, y2, k1, k2, e to the pi k3 dot x of y3, e to the pi k4 dot x of y4, and then just the expectation value of this. Okay. So as not to make mistakes with factors of 2, we just look up the answer that we once computed. It's reported in Pulchinski. Just look it up. Here, it is Yij to the power 2 alpha prime ki minus kj. Ki minus ki dot kj. Okay. So, now what we're going to do is to trust that the position dependencies will cancel and just work with standard format associations for y1, y2, y3, y4. Okay. So, let's say that we put y1 at 0, y2 at 1, y3 at infinity, and y4 somewhere. Okay. So suppose we put y1 at 0, so we've got this line, y1, y2, y3, and then y4 anywhere. Now this y4 is going to be integrated over the whole real line. So notice, of these 6 possibilities, in integrating y4 we're going to realize 3. Because if y4 is here, we get one cyclical ordering. If y4 is here, we get another cyclical ordering. Y4 is here, we get another cyclic. This is the same as that because it closes up. Oh no, we've got, this is infinity, so there's no y3. Right? Here, here, and here.
Yes.
3 cyclic orderings. Right? Had we chosen y3 to be a fixed point, it would have been. We'd have this plus that to the right would have been the. But we're not, we're choosing infinity. Okay, so we've got 3 cyclic orderings. To get the other 3 cyclical orderings, we could interchange y1 and 2, for instance, and then do the same integral. Okay? So, each of these will come with distinct factors of the traces. So, we break up the integral into, depending on what range the integrand lies in. Is this clear? Okay, so let's for instance take this case, the case where y4 lies between 0 and 1. Okay, so let y4 equals t and let it lie between 0 and 1. Okay, so what are we going to get? Let's say also that these guys are the fixed vertex operators. And so all the Seeghorst dependence is going to give us some factors of infinity, which will cancel other factors of infinity from this t with whatever. Actually, let's just see how that works. Let's see how the infinity cancellation works. Okay, the Seeghorst dependence is what? It was C1, it was C, and now I'm going to call it, depending on where they inserted, 0, 1, C 1 infinity, and C infinity 0. right? y12, y13, y12, y23, let's say y. y01, y1 infinity, and y infinity 0. Right, the three differences. Okay, this guy is 1, because it's 0 minus 1 or 1 minus 0, whatever, some sign. And this guy is basically infinity square up to a sign. Of course, we'll regulate infinity in the usual way to give that meaning. Okay, now what we're supposed to get from here. Well, let's see what we get from here. From here we get, or let's look at all the contractions involving k, the guy at infinity, k3. Okay, so the guy at infinity, all these yij's are infinity. So we get infinity to the power 2 alpha prime k1 plus k2 plus k4 dot k3. Right? But k1 plus k2 plus k4 is minus k3. So that's minus k3. So that's infinity to the power minus k3 dot k3. Now k3 dot k3 was plus 1 by alpha prime. Right? Because it's negative mass, but k3 dot k3 was minus m square. So plus 1 by alpha prime, so that's to the power minus 2. And that cancels this. Okay? So that tells us that we can forget about the C ghost contribution and the contractions here involving infinity. So we need only worry about the contractions not involving infinity. Okay? So let's look at those contractions. So I only worry about the contractions not involving the point y3. Okay? So the contractions not involving the point y3, there's y12 times something, but you know 1 to the power anything is 1. Y12 is 0 minus 1, so that we forget about. There's y13 and y23, those involve infinity. So all that we have to worry about are the things involving 4. 1 and 4 and 2 and 4. Okay, so there's y14, and that had 2 alpha prime k1 dot k4, but y14 is simply t, because it's t minus 0 up to a sign, yes. And then the other guy is 1 minus t. Okay, and that will be 2 4. 2 alpha prime k1 dot k2 dot k4. Okay, now let us immediately write this. So that's, and then what we need to do is integral dt. Then what we need to do is integral dt, and that is basically our answer for the part of the contribution in this range. Okay, now let us check a couple of things. Firstly, it's good to write this in terms of the invariance. Okay, but k1 dot k4 is equal to k1 plus k4 the whole thing squared minus k1 squared minus k4 squared by 2. Now this is minus u, right? Because our conventions were minus, yes. So that's minus u, and this is plus 2 over alpha prime by 2. Right. So 2 over, okay, let's write it like that, by 2. So maybe what we'll do is to put 2 by alpha prime and an alpha prime u here.
Yeah. The x.
The thing that we've seen before, or maybe the open string version of it. Similarly, the other guy, 2.4 is same as 1.3, and so what we'll get is S.
1.3 is T.
Sorry, 1.3 is T. Thank you, thank you. So we'll get minus alpha prime T plus 2 divided by 2 alpha prime. Those are the powers. So let's, but there was a 2 alpha prime here, so that cancels the 2 alpha prime. Okay, and therefore what we get is T to the power 2 minus alpha prime U, 1 minus T to the power 2 minus alpha prime T. Now we don't want two T's, so we'll call this Y. Okay, and that's that. But all of you know about this lovely formula, right? X to the power A, 1 minus x to the power b is from x ranging from 0 to 1 is this thing that people call the beta function, which can be written as products, ratios of gamma functions. Right, all of you know about this. So I'll just remind you that this thing that people call b of ab is equal to integral dx x to the power a minus 1, 1 minus x to the power b minus 1. Integral 0 to 1. It's sorry, I got something wrong. Yeah. Where? You're saying I got the relative sign wrong? Let me check. Let's see. We got k1, let's say k1 plus k4 squared minus k1 squared minus k4 squared by 2.
K1 squared is 2 over mod.
You're right. K1 squared is positive because it's minus of mass, but the mass is negative. Yeah, you're probably right. So this is positive. This was negative.
It was minus.
Minus. So there was an overall minus. Minus. Yes, you're right. Minus 2. Thank you. Okay. So this is this beta function which, all of you have shown in your math methods course is equal to gamma by gamma into divided by gamma, right? So
Gamma A, gamma B over gamma A plus.
gamma of
Or maybe answer.
I think gamma of argument minus 1.
No.
Is it just gamma?
No, I think it's
Gamma A, gamma B.
Gamma A, gamma.
gamma A, gamma B over gamma A plus B.
Gamma over gamma A plus. I think you're right. Thank you. I think you're right. Yes.
Another proof of why gamma half is square root of pi.
Excellent. Excellent. Okay. So now we're just going to use this formula where A is whatever it is. So now let's see what is A. We wanted to write A minus 1. So the effective value of A here is alpha prime u minus 1. Plus 1. No.
Minus of alpha prime u plus 1.
Minus of alpha prime u plus 1, yes. Alpha prime u plus 1 and minus of alpha prime t plus 1. Now, no doubt Polchinski has defined this as something like he likes to do. Let's see. Yes, he has defined alpha of x is equal to 1 plus alpha prime x. Okay, so then this becomes, we've got beta of minus of alpha prime alpha of u and minus of alpha of t, which is equal to gamma of minus alpha u, gamma of minus alpha t divided by gamma of minus alpha u minus alpha t. And then of course you can write this out in terms of u and t. So there are these extra. So this will be minus alpha prime u minus 1, minus alpha prime t minus 1, and this will be minus alpha prime t minus alpha prime u minus 2, and then you could write that in terms of s if you want. Yeah, perfect. Okay. Now, there are two more integrals to do. There are two more integrals to do.
Minus infinity to 0.
Right. But you know the integrals, you can more or less guess what you're going to get. Just by ST permutations. Okay. So let's see. So let's look at that. Here, why did we get u and t? We got u and t because the non-trivial OP coefficients involved k1 dot k, k1 dot k4 and k2 dot k4. Okay. In this case here,
actually, because plus infinity is essentially equivalent to minus infinity.
yeah.
So when it's on the left of y1, it will be between 3 and 4 and 1 and 4.
Exactly. So let's think of it this way. We have
Yes.
exactly. We have three vertex operators. Okay, and when we put the guy that is integrated between 1 and 2, so let's call this 1, 2, 3. We put the guy that was integrated between 1 and 2. What we got was we got 1 with 4 and 2 with 4. So that's the rule. The rule is you will get the objects that come with the guy you're integrating and its neighbors. Okay?
What it's being integrated between.
Exactly. So now let's write this out. So what have we got so far? We had 1, 2, 3 fixed and we put a 4 here. So let's be careful because that is trace of lambda 1, lambda 4. Let's do it that way. Say that our convention is anti-clockwise. Lambda 1, lambda 4, lambda 2, lambda 3. Okay? Times beta of minus alpha u minus alpha t. By the way, the beta function is symmetric between its arguments, so it doesn't matter which one you put first and second. Okay. Then when we put 4 between 2 and 3, we will get plus trace of lambda 1, lambda 2, lambda 4, lambda 3 times beta of now 2, 4, which is same as 1, 3 minus alpha t, and we will get 3, 4, which is 1, 2, which is minus alpha s. Okay, plus trace of
There's only one combination left.
exactly lambda. So now when we got this here, lambda 1, lambda 2, lambda 3, lambda 4, beta of, now we have 4, 1 and 4, 3, exactly. So minus alpha u minus alpha s. These are 3 of the answers. However, they're not the only 3 because we put 1, 2, 3 in this order,
Yeah.
but there's also the choice where we put 1, 3, 2.
Yes.
So let's work that out. We have 1, 3, 2 Okay, so suppose 4 is here. Okay, now what we're going to get is 4 1 and 4 3, which is same as U and S, but that we already have here,
Yes.
except
The trace will be different.
the trace is different, exactly. So now we're going to get this with
Probably
1,
some anti-committed.
exactly, 1 4 3 2. Okay, 1 4 3 2. So now here we have 1 2 3 4. Okay, so I want to check whether this is the same as trace of and this was okay, so what we get, okay, let's first write it out. This plus, I'm just writing the order, 1 4 3 2. 1 4 3 2 gave us this. Then there was this guy. So let's write it out like this. This was 1 2 3 4 plus 1 4 3 2. Oops, sorry. Does somebody remember what this was before I rubbed it out?
1 to 4 trace, 1 to 4.
1 2 4 3, and we'll write 1 4 3 1 4 2 3 up here. 1 4 2 3. Now let's look at the guy where we put our cross here. This will give us forward 3, which is the same as 1 with 2, so that's S, and forward 2, which is 1 with 3, which is T. So that's S and T, so that's with this guy, and comes 1 3 4 2. Okay, and then there is the quantity that comes from here. That's when this is here. That's forward 1 and forward 2. Forward 1 is same as is U, and forward 2 is T. So that's this, and so that's 1 3 2 4. So that's our full answer. Okay, now we want to take this answer and write it in the nicest possible way, and I want to give you a claim. The claim is that no, just let's leave this like this. Okay. Now, the last thing I want to say about this structure is the following. Look, you remember that we had this way of relating the normalization factors behind vertex operators from unitarity. Do you remember when we looked at closed string scattering? We wanted to know what is the normalization factor behind the tachyon, for instance. And then we used the fact that that the 3 tachyon factors, 3 tachyon vertex which we could compute came with 1 factor of the normalization. The 4 tachyon scattering came with 4 factors of the normalization. Both of them came with the same partition function on the sphere. Okay, but this had to factor on poles. So if we went and sat on the pole of the tachyon, it had to be proportional with a product of 2 3-point functions. So we got 2 factors of partition function on sphere times 6 factors of the unknown normalization was related to something with 4 factors of unknown normalization times 1 factor of partition function on sphere. And so we got a relation of the form G squared CS2 was equal to something particular, some known number. And then we talked about how this was at the moment just some triviality, relating one number to two unknown numbers. But if you did it for everything, it was highly constrained, and it all worked out. That also the relative coefficients were the same as from the state operator map. You remember that discussion, right? Okay. So in a similar way, we can undertake the same discussion for tachyons, open string tachyons. It's just basically identical discussion. However, there's something interesting now when we add the Chan-Paton factors. Because if unitarity worked without the Chan-Paton factors, That's Bandhu. No, I'm still teaching my class, but in 5 minutes I'll leave. I'll come home early. Hey, remember, we have to. Yeah, okay. I'm going to have to go soon. Sorry, my son has a test tomorrow, which he wants me to. Okay. Okay. So the additional thing that we want that we have to now check is that if unitarity worked for tachyon scattering, so let us assume that with U1 tachyons, this for tachyon scattering was unitary. Now, is it still unitary with UN tachyons? You don't get to choose now. You know, you've got your vertex factor, the factor behind your tachyon determined once and for all. It just has to work. Okay? So it's, you see, everything else is the same. It's only the dependence of the Chern pattern factors. But we know what the 3-point functions are like. The 3-point functions were of the form lambda 1, lambda 2, lambda 3. Okay? So, if it's going to work, it has to be that these additional factors of this plus this is exactly what is needed to be the residue of two 3-point functions. Now notice that this 3-point function is one in which is diagonal in Chern pattern factors.
So this one trace.
Exactly. So how does it work? What works is that this lambda 3 is summed over everything. So that basically becomes identity.
Identity exchange.
You know, what I'm using is that if you've got a vector space and you've got some operator and you have lambda and lambda O prime, and then you sum over all lambda, you have completeness.
Yes.
So that's just O prime. So when you do that sum, if you've got, let's say, so, right. So suppose we had lambda 1, lambda 2, lambda 3, lambda 4. You do that sum, what we will get here is that lambda 1, lambda 2, this was some lambda tilde, right? Because that's what's being exchanged.
Summed up, yes.
Times lambda 3, lambda 4. That anti-commutator. Now, I'm leaving this as an exercise for you guys. Do that carefully. Check that you get the right, and that this anti-commutator square works with the right indices and with the right number. Factors of 2 all work out. So that what you get for this 4-point scattering here, the Chern pattern independence, is exactly what is needed from unitarity. Okay? But please work this out. It's a simple exercise, but please work this out. Last thing I wanted to say about 4 tachyon scattering is that there is a sense in which it is not as nice as 4 graviton scattering. And why is that? You see, as we've often discussed, one of the really nice properties of scattering amplitudes is invariance under permutations. Right? If we permute the external labels 1, 2, 3, 4, you should get the same answer if the scattering particles were basically identical. Now, in the case of the bosonic string, the invariance under permutations happened in some sort of miraculous way, in the following sense. There was one answer which was manifestly invariant under permutations. That was fine. But if we expanded it in poles, there was one expansion of the answer in which you expanded in S-channel poles. Another expansion of the answer in which you expanded in T-channel poles. Okay? And those two expansions were expansions of the same function. Okay? And so somehow miraculously you took the first expansion, you did the sum, and you found that you could have actually taken that final answer and summed in T-channel poles and got the same answer. Okay, that there was a representation of the whole answer in terms only of sums over S channel pools. This is a remarkable thing. In a normal Feynman graph, how does scattering happen? How does this permutation symmetry happen? It happens because you've got these kind of graphs. You've got this graph. Let's say this is 1, 2, 3, 4. But then you also have the graph which goes like this: 1, 3, 2, 4. And then you'll also have the graph that goes, other one's harder to draw with. Yeah, going around. But you have these three different graphs. And then they manifestly, you take one graph to the other. So you're adding three different pole contributions. So of course it's permutation symmetric. What's the big deal? Okay? The thing about the closed string was that there was a representation of the answer only over sum over S channel poles. And you might have thought, this is crazy, because it's violating a basic rule over scattering amplitudes. There has to be permutation invariant. Look, you've got sum over S channel poles, but you've got no T channel poles. How the hell could it be permutation invariant? But it was in sum over an infinite number of S channel poles.
You're saying it is giving 1 by 1 minus x.
Exactly. And when you, the coefficients, as we discussed, if you remember, of each pole was a polynomial in T. But when you did the sum, you found an answer that had poles in T. And in fact, there's an equivalent representation of that same thing, only in terms of T channel poles. That was a very beautiful thing about closed string scattering. On the other hand, here it's more ugly, because it's more like Feynman diagrams. The final answer is not one object, it's a sum of three objects, which are permuted. So permutation is no mystery. It's like Feynman diagrams. Okay? So there's a sense in which open strings behave more like traditional field theory. Closed strings are more beautiful. Things happen in a more mysterious way. And this is connected surely with the fact that closed strings talk about gravity, while open strings in the end don't at tree level. Okay? So the closed, open strings are often what people do for toy examples, but to really understand gravity, there are qualitatively new features in closed strings. We see already at the level of tree level amplitudes. This feature, by the way, was responsible for the birth of string theory in some sense, because people were looking for, people studying QCD amplitudes had this feeling that perhaps you sum poles of one sort and you'll manage to get the other. And Veneziano, but really Virasoro-Shapiro, wrote down the amplitude just as a guess for something that would have this property. And then that guess then led to the birth of string theory. It remains one of the really beautiful features of the theory that I don't think we've completely understood all aspects of. Okay, fine. Let's stop here. I think this is all I wanted to say about just tree level scattering. Of course, we could go on. We could do amplitudes in the heterotic string and so on. But it's getting boring, right? I mean, you guys know the methods. You can apply them. We'll focus now on the physics. So in the next class, we'll move on to chapter 7 and the superstring version of that. That is, we'll talk about one loop amplitudes. One loop amplitudes. We'll talk about unoriented strings and keep going.